Hi friends, welcome to the second video regarding the subject Introduction to Vibrations, which is the fifth module of Dynamics of Machinery. Now in this video, I'll take you through a few important terminologies and definitions which is required or which is important to keep in mind while studying this subject in detail. And after these definitions, we'll go to free vibrations topic, and within that subject we'll study about how to arrive at a governing equation for a free vibrating model. And from the governing equation we will go to how we can arrive at or derive the displacement equation for that particular governing equation. And after that topic, the third one, we'll discuss about the natural frequency of vibration of the system and different methods of finding those natural frequencies. Now, let us start with defining mass, stiffness and damping. What is the significance of mass, stiffness and damping with regards to a vibrating model? See, these three are the major, most significant components in the mathematical model of a vibrating system. See, a vibrating system definitely should have a body which is always vibrating. That is the body with mass. Now mass tends to make us understand about the motion of a rigid body. So as it is moving, vibration means motion. So it is always moving. That means it always stores kinetic energy. Now there should be a component which should cause that motion or vibration. That is the flexible spring which will be attached to that particular mass. Now with regards to spring, we will define the term stiffness. It offers or gives us the deflection of a flexible component or the spring. Now this always stores potential energy. Now the mathematical model has a body which is vibrating as well as has a component which causes this vibration. Now to arrest this vibration or to reduce this vibration, we will be fitting in a damper with the system. Now the term damping tends to make us understand about the absorption of this vibrating energy. So the symbol of the damper is also given. It is a symbolic representation of a piston working inside an open cylinder. Now take the example, take the figure in the right side. It is some kind of a compressor or a centrifugal vibrating machine which is fixed on a fixed horizontal surface mounted on two flexible rubber objects. Now these rubber objects acts as a flexible string as well as a damper, and the vibration occurs or the motion of the body occurs vibrates in a vertical axis. Now the displacement or the small vibrations which occurs, that means from the mean position the body will be displaced. That particular displacement is given as x, which is given in the upside arrow. It is a function of time. Now this real-time object can be modeled into a mathematical model using a mass, spring and damper, which is shown on the left side. Pay attention closely to that particular system. Such a system is known as a mass, spring, damper model. It is the mathematical model which we draw or which we arrive at while we do the vibration analysis of a real-time vibrating body. Now when we consider this vibrating model, we can define a few more terms. First one is amplitude. See, on the left side of the figure there is a vibrating body given which is mounted on two flexible springs and attached to a horizontal basis or foundation. Now the datum line O represents the mean position, and negative A defines the two positions to which the body will be displaced vertically. Now the displacement here or the value of that particular displacement is given as x, which is a function of time. Now amplitude will make us understand how far the mass displaces from the mean position O to A or from O to minus A. Now when we defined amplitude, a related term frequency can also be understood. How fast the mass goes in one cycle from 0 to A, then to negative A and back to the initial position of 0. That defines frequency. One complete cycle in 1 second is exactly the value of frequency, which is always given in the unit of hertz. Let us come to the term phase. Now if the same vibrating model, one end I termed as P and the other end I termed as Q, and the motion is occurring across the points P and Q. That means if the position of P is going downwards, the position of Q is going upwards. In a longitude, in a transverse way, if the body is vibrating, we can say that P and Q move out of phase, or there is a 180-degree phase difference to the movement. Now let us represent this displacement using a periodic function. X of t is equal to a sine omega t plus phi. Here the sine term always is given only to make us understand that this is a periodic oscillating or harmonic function, harmonic kind of motion which is occurring, where the capital A defines maximum amplitude of that particular displacement, how much level it can be at, it can move from its mean or datum position. Then omega defines the frequency in radians per second. The relation between omega and f, which is also frequency in hertz, is given as omega is equal to 2 pi into f, and the term phi always defines the phase difference. Phi, if it is given in radians, we can convert that as 180 degree into 180 degree by pi into degrees. Now if we plot a graph for that particular equation, x of t is equal to a sine omega t plus phi, for phi equal to 0, the graph will be kind of a sinusoidal function. That should be obviously a sinusoidal function. Now the the distance between two successive amplitudes will be 2 pi, and how the 2 pi is occurring is given in the right hand side, the equation which is written. Pay close attention to that one. And now if we consider a second graph plotted with same kind of equation for two curves, first one is P and the second one is Q. That means the difference between, distance between the happening of the two successive vibrating models is, it is given as pi by 2. Then we can say that Q, the curve Q lags the curve P by pi by 2. Pi by 2 is the phase difference there. A few more definitions, we'll go through a few more definitions. Now vibration can be defined as the to and fro motion from a mean position, or the repeated periodic motion occurring due to the action of a force. Such definitions can be given to the term vibration. Now time, what is time period? The time required to complete one complete cycle of this particular motion. It is either denoted by capital T or small t. Now frequency, what is frequency? The number of cycles that is occurring per unit time. It is given as small f. Relation between small f and time period t is given as it's reciprocal. F is equal to 1 by t. Amplitude we have already discussed. See, to understand amplitude in a much better mathematical model way, consider a simple pendulum which is hanging from a roof. Now the angular displacement theta, or that means the maximum angular displacement which it can cover in one cycle, or to the maximum datum which it can surpass, is known as theta, the angular displacement. It is also the amplitude of that particular swinging pendulum. Now if we come across that is a rotational case. Now if we consider a linear case, a translational case of a spring and mass system, the mass is hanging from a spring from a roof. Now due to the weight of the mass, it will be having an initial displacement of x, which is on that particular x is also the amplitude of that vibration, that displacement. Let us discuss about degrees of freedom. What is degrees of freedom? See, degrees of freedom specifically for this vibrating model. Consider three figures. The first figure consists of a mass and a single spring. Now to define that particular motion of the mass or that particular system, only one single variable x1 is enough. The value of x1, the equation of x1, if we know, we can define that particular system. Hence that particular mathematical model or vibrating system is known as single degree of freedom system. Consider the second figure. It consists of two springs and two masses. The displacement of the two masses depends on many factors. That means the value of m1 and m2 for the start, then the values of k1 and k2, which are the stiffness of those springs, that depends on the material of the spring, type of spring, etc. So to completely define that particular system having two spring and two mass, two displacement values or equations should be known. One is x1 and x2. Hence that system is known as 2 degrees of freedom system. If we convert that particular example into a swinging pendulum case, instead of hanging the pendulum bob from a stretchable string, if we attach a spring to that particular roof and we hang a bob from that spring, now to completely define that particular system, we have to know the deflection that is being caused on the spring, which is x, as well as the angular displacement of the bob from the mean position, that is theta. Hence that system is also a second degree of freedom system or a 2 degree of freedom system. Now consider a cantilever shaft which is attached to a vertical roof. If we give an initial pull to that particular shaft, the cantilever portion, the change or the deflection occurring is represented in that figure. Now to completely define that particular displacement which is occurring to the shaft, we have to know the displacement of deflection caused on each point of the shaft. Now, and also that particular displacements for each point on the shaft will be different from each other. Hence, such a system can be defined as an infinite degrees of freedom system. What is damping? Damping is the resistance given to a vibrating body. A body with infinite degrees of freedom is known as a continuous system. A body with finite degrees of freedom is known as lumped system or a discrete system. Now, in mechanical vibrations or inside the topic, a mechanical system is a system which is having a mass, spring and damper. Now, the analysis of a vibrating body or a vibrating system is always classified into 3 stages. First stage is mathematical modeling. A real-time vibrating body or a system is initially modeled into a mathematical system using a mass, spring and a damper system. Now the second phase is, after mathematical modeling, we have to derive or come up with a governing equation which defines the motion of that particular vibrating body. And after derivation of the equation or governing equation, we have to solve that particular equation using different methods. Most probably we'll go with differential equation methods. And we can interpret the results numerically, as well as we can plot different graphs and get different results. That is the solution part of the analysis. So when we cover up these 3 stages in an orderly manner, what we are doing is nothing but analyzing a vibrating real-time system. This is the vibration analysis procedure which I have represented here. Now let us go to equations of motion. Let us consider 2 systems. One is translational and one is rotational. Both the systems are undamped. That means no damper is connected to the system. For the first one, that is translation motion, we have a mass and a spring. The mass is tending to move on a horizontal surface. Now if there is no motion to this system, total forces acting on the system, summation of F should be equal to 0. Now with the motion, that means if the mass is either moving towards right or left, there should be an inertia force acting opposite. That means summation of force sigma F should be equal to m into A. What is A? A is the second derivative of the displacement x, which is shown there, dx square by dt square. That particular value dx square by dt square can be termed as x double dot. See, x is the displacement. If we differentiate it one time, we will obtain velocity. That is represented by x single dot, x dot. If we further differentiate that one, we will arrive at acceleration, that is d square x by dt square, which is denoted by x double dot. Now as it is attached to a spring, it will introduce a kind of resisting motion to that particular inertia. That is known as a spring force, which acts in the opposite direction. The spring force is nothing but k into x. The spring force is always proportional to the displacement x, and the proportionality is changed into an equation introducing the stiffness constant k. So finally we arrive at the equation mx double dot plus kx equal to 0, which is nothing but the equation of motion of this particular translating vibrating body. Now convert all the things into a rotational motion scenario. We have a rotating disc or a shaft, rotating disc which is keyed to the roof using a shaft. Now the rotational equivalent of mass here will be J or I. J is polar moment of inertia, I will be moment of inertia. You can either use J or you can use I. Now we had a spring which is the energy storing device or potential energy storing device. Same way we have a shaft here which is the energy storing device. Now both stiffness of the spring and shaft is denoted by K. Now instead of having a translatory displacement X, we have a rotational displacement theta here, angular displacement theta. Now before twisting, the total summation of moments or here will be equal to 0. After twisting, that should be equal to J into theta double dot, J or I. You can use either the term J or either alphabet I. Now, what is theta? Theta was angular displacement. So, first derivative theta dot will be velocity. Second derivative theta double dot will be acceleration, angular acceleration. Now, resisting this kind of motion, resisting force will be applied by the shaft, that is the spring force, which is equal to K into theta in the opposite direction. Hence, we will obtain the equation of motion in the case of a rotational moving system as J theta double dot plus K theta equal to 0. This is the equation of motion. Guys, I am going a bit faster only to reduce the length of this particular video. You can simply go through the video once again and write down all the equations or necessary points from this video. Thoroughly understand what we are describing here. We have three methods of vibration analysis, and for a free vibrating body or a natural vibrating body or an undamped natural vibrating body, the vibration analysis is majorly to find out the natural frequency of vibration. First one is energy method. In energy method, for a vibrating body, we assume that the total energy of the system always remains as a constant. For an undamped system, we have two components in the vibrating body. One is the mass component, which will be moving, hence kinetic energy is associated with that particular body. Next one will be the spring, which is the energy storing device, so potential energy will be related to that of the spring. Kinetic energy of a mass, of the moving mass can be represented as half into mx dot square. We have the equation for kinetic energy is what? Half mv square. What is v? Second derivative of x. What is x? X is the displacement. So second derivative is denoted as x double dot, as I said previously. And potential energy is associated with spring. So we will introduce the term stiffness constant K in that particular equation, and it is given as half kx square. Now differentiating that particular equation with respect to time, see the differentiation procedure. We are applying chain rule. For example, x dot square can be differentiated as 2 into x dot, then multiply it with the differential of x dot, which is x double dot. So it will be 2x dot into x double dot. Hence we arrive at equation number 1, which is mx double dot plus kx equal to 0. This is the same equation that we have derived previously. Now let us assume the displacement occurring here is a harmonic or a oscillatory displacement. Hence x can be written as a into sine omega t. See, sine term is given here only to symbolize it as a harmonic motion or an oscillatory or a periodic motion, with a as the maximum amplitude of that particular motion or displacement. Now x dot, which is the first derivative, will give you the velocity, which is a into omega into cos omega t, differentiating the equation for x equal to a sin omega t. X double dot will give you the second differential, which will provide you with the acceleration value, which is equal to, again differentiating, minus a omega square sin omega t. Now substitute the values of x dot, x double dot and x in the governing equation, which is equation number 1, mx double dot plus kx equal to 0. We will obtain, see the substitution, carefully substitute for the values there, and finally we will get the equation as minus m in omega square plus k equal to 0, because sin omega t and a, capital A, was a common term there, we can cancel it out. From that equation we can write omega square is equal to k by m, and omega is equal to square root of k by m. Now omega is the angular velocity, which is expressed as radians per second. Now this particular value of omega is nothing but the natural frequency of vibration of this undamped free vibrating body. And if we find out or write the term omega for natural frequency, the unit will be radians per second. But The natural frequency should also be expressed in terms of hertz, which is denoted by the alphabet small f. Now the relation between small f and omega is f is equal to 1 by 2 pi into omega. Hence we obtain f is equal to 1 by 2 pi into square root of k by m hertz. So whenever you are asked to find out natural frequency of vibration of a body, vibrating body, you should definitely find out the answers both in radians per second as well as in hertz to be in the safer zone. Now the second method for finding out this natural frequency of vibration is Rayleigh's method. Here total energy of the system is always equated to the maximum potential energy. See, the total energy is always the sum of what potential energy and kinetic energy. Now, whenever kinetic energy is maximum, potential energy will be minimum, and vice versa. When potential energy is maximum, kinetic energy will be minimum. So, total energy at its maximum will always become kinetic energy maximum. Now, in Rayleigh's method, total energy is equated to what? Maximum potential energy. Hence, we can write kinetic energy maximum value should be equal to maximum value of potential energy. Kinetic energy is given as half into mx dot square. Kinetic energy is associated with the moving body, which is mass, and potential energy is associated with the energy storing device, which is the spring, which is written as half kx square. Now x dot square is nothing but a omega square. How we have obtained that one? We are discussing about the maximum value. See, x dot is a omega cos omega t. We have derived or differentiated that particular value in the previous energy method also. So maximum value of x dot will be obtained when the cos omega t value is equal to 0. Hence, the maximum value of x dot square is given as a omega whole square. Similarly, maximum value of kx square is given as k into a square. X is equal to a sin omega t. Maximum value of x is what? When sin omega t becomes 1. Hence here also we arrive at the same equation, m omega square is equal to k, from where we can find out the natural frequency of vibration. Omega is equal to square root of k by m radians per second. See, in few textbooks omega will be denoted for natural frequency, and other textbooks omega suffix n, omega n will be denoted for natural frequency. Whatever the case be, both the values will be same. Whenever you are using the term omega or omega n, clearly mention what you are denoting that particular term for. The third method for finding out the natural frequency is equilibrium method, which is also known as Newton's method. Here, the equilibrium of forces is considered. It is a simple method or simple concept. We have been using equilibrium method previously in different subjects also. Mx double dot plus kx equal to 0. It is one equation. If you provide a damper, mx double dot plus cx dot plus kx equal to 0. You will understand these equations clearly when we discuss about damped vibrations cases. And the last one, mx double dot plus cx dot plus kx equal to f. Now in the equations 1 and 2, right hand side you had 0, and in equation 3, right hand side you have f. Now the difference is, first two equations were for free vibrations. First one specifically for free undamped vibration, second one for free damped vibration. But the third one you are having on the left hand side, in place of 0 you have a term f. F denotes the external force which is given. That means that is the scenario of a forced vibrating body. See, if you hang a mass from a spring and a damper and you freely allow it to vibrate, that is the case of free vibration. If you remove the damper there, you only remain with a mass and a spring. And if you simply leave it to vibrate, it is again the case of a free vibration undamped system. If you attach a damper, it is a free vibration case of damped system. Now after the free vibration, again if you are going to hold the mass and pull it down a little bit and then leave it, what are you doing there? You are simply applying an additional external force. That particular external force is given as capital F in the third question. So that scenario becomes vibrations of a forced damped condition. You will understand it in the upcoming videos and sections. For the time being, equilibrium method means we are arriving at these three kind of governing equations. Now, to clearly understand these three methods or the methods used for arriving at the natural frequency, let us look into two sample examples. The best method which can be used to solve problems is energy method. See, look the first figure given here. You have a rotating pulley or disc. One side of the pulley you have a spring attached to a horizontal surface. Now the spring is given with a spring constant K. Towards the left side of the pulley you are seeing a mass which is hanging from the pulley. The mass is small m, spring constant is K, and mass of that particular pulley is given as capital M. Radius of that pulley is R. Direction of rotation is also given. How is that particular direction possible? It is happening due to the mass which is hanging. So freely the mass will slowly come down a little bit. That means it will be displaced. That particular displacement is x, which is given in the downward direction. We are asked to find out the natural frequency of vibration of the given system. Let us apply energy method. What is energy method? Total energy of the system is considered to be always a constant. Total energy means what? Whatever components are there in the system, the energy is generated in all the components you have to add up, and that should be equated to a constant. Let us take up the components one by one. First one is mass. Mass is what? The vibrating body. So the vibrating body always has displacement. It moves, and definitely because it has mass there will be an inertia force. Now as we are discussing about the energies, the mass which is moving is associated always with what? Kinetic energy. So the kinetic energy related to mass is given as half into mx dot square. X dot is nothing but velocity. First derivative of displacement x. Now consider the spring K, which is the vibration causing element. It always stores energy, potential energy. So the energy associated with spring is nothing but potential energy. That equation for potential can be written as half into kx square. That is the third term in that equation. The middle term, let us look into the middle term. See, apart from mass and spring, you have a rotating pulley also. It is a rotational system, not a translation system. See, for the mass, the displacement happening is translational, vertical. For the spring, the deflection happening is again vertical, upward direction. But for the pulley, the displacement happening is rotation. So angular displacements are occurring. Hence, without going for taking in place of linear displacements or translation displacement x, you should be giving the term theta there, angular displacement. Remember the rotational body and the equations which we have written for that rotating disc hanging from a shaft. So theta is the angular displacement, theta dot will be the angular velocity, and in place of m mass, the rotational equivalent we will take it as I, which is moment of inertia. Hence the second term is half into I into theta dot square. As the body is rotating, it is again associated with kinetic energy only. So totally the equation will become as half into mx dot square plus half into I theta dot square plus half into kx square, which is equal to constant. Now we can slightly modify the equation. In place of the terms x and x dot, we are converting that one in terms of theta. Now look into the second figure here. The rotating disk is separately shown, and from one side the displacement of the mass x is also shown. Now the rotating disk has radius of r and the angular displacement is shown as theta. So the translational or the linear displacement x can be equated to r into theta. Hence the first derivative x dot becomes r into theta dot. So substituting this x equal to r theta and x dot is equal to r into theta dot in the first governing equation, we can rewrite the equation as half m r dot square theta dot square in place of what? X dot square, plus second term remains the same, half into I theta dot square, plus in place of x square for the third term, use r square theta square. Now differentiate this rewritten equation with respect to time. We will obtain half into mr square multiplied by theta dot square, the differential will be 2 into theta dot into theta double dot, applying chain rule. Plus second term is again differentiating what? Half into I will be constant, theta dot square, it will be again 2 into theta double dot, and the third term half into kr square is a constant, differentiating theta square will be 2 theta into theta dot. In all the three terms, half 1 by 2 is common. In all the three terms, 2 is common, and also theta dot is also common. Cancelling out all the three common terms, we remain with the equation mr square theta double dot plus I theta double dot plus k r square theta equal to 0. Now rearranging the terms with theta double dot and theta, we have mr square plus I common, theta double dot plus k r square theta. Now I can be written as m half into m into r square, because capital M is the mass of the rotating disk and r is the radius of particular disk. So I, which is the rotational equivalent of mass, can be written as half into capital M into r square. Hence the equation is rewritten aborting the value of I and introducing half into m into r square. Let that be equation 1. Now let us compare this equation 1 with the standard equation for a vibrating body, which is mx double dot plus kx equal to 0. X double dot, theta double dot, compare the equations, and x and theta both are there. So terms coming with x double dot is m and x is k. In that particular standard equation, how we have obtained that natural frequency omega n is nothing but square root of k by m. What is k? The term coming with x. What is m? The term coming with x double dot. Now let us look into the equation number 1. For x double dot, the term is theta double dot there, and for x the term is theta there. So the term coming with theta is kr square, and the term coming with theta double dot is mr square plus half into capital M into r square. Hence omega n square can be written as the ratio of that term with theta in the numerator and the term with theta double dot in the denominator, which is kr square by mr square plus half into capital M into r square. Again, multiplying it with the 2, you will get 2 kr square divided by 2 into mr square plus capital M into r square. If it is omega n square, taking the root, you will obtain omega n, which is square root of 2k by 2m plus capital M radians per second. As I had mentioned earlier also, if natural frequency is asked, then you have to definitely find out the value of natural frequency both in radians per second as well as hertz. This is only to be in the safer zone. So Fn is nothing but 1 by 2 pi into omega n. Substitute the value of omega n, find out Fn. Let us move on to one more example. I'll read out the question. You please look into the figure. A circular cylinder of mass 4 kg and radius 15 cm is connected by a spring of stiffness 4000 Newton per meter as shown in the figure. It is free to roll on a horizontal rough surface without slipping. This is the important sentence here. The disc cylinder is free to roll on a horizontal rough surface without slipping. Determine the natural frequency. As soon as you emphasize that particular sentence, you can understand that the cylinder has two kinds of motion. One, it has a translation motion. Just as we drive an automobile, how the wheel of the automobile moves. See, at starting of the journey, the vehicle will be at one place, and after 5 minutes the vehicle will be at some other point. How is it happening? Only because the wheels tend to displace itself, and while displacing from one position to the other, the wheel also rolls on its own axis. So the cylinder has rotation motion as well as translation motion. This should be always kept in mind, because understanding this is the significant portion of this particular numerical. Again, let us employ energy method here. Total energy of the system is remaining constant. Now let us start with spring. Spring is what? Energy storing device. It is associated with what? Potential energy. So with respect to spring, we can write the energy equation as half into kx square. Now consider cylinder. Cylinder has two kinds of motion, as I had said earlier. It has translatory motion as well as what? Rotatory motion. So for translation, let us consider the mass of this cylinder. Hence, it is translating, it is associated with kinetic energy. That equation is the first term here, half into m x dot square. What is x dot? X is the displacement occurring and x dot is the velocity. Now, as the cylinder has rotatory motion also, the rotatory components also should be considered. That means the rotatory equivalent values should be considered here. That is the second term, half into I into theta dot square. In place of x, which is the linear displacement, we have theta, which is the angular displacement. And the rotational equivalent of mass m is taken as I here, moment of inertia. Elaborating that equation, we have half into m into, in place of x, we are substituting r into theta as in the previous question, and for theta dot we have r into theta dot. Hence x dot square will become r square theta dot square will remain the same, and x square will become r square theta square. Now taking the time derivative of this elaborated equation and applying the chain rule just as in the previous numerical which we have done, you get the lengthy equation there with three terms consisting of theta dot and theta double dot. Now 1 by 2, 2 and theta dot are common in all the three terms, which we can take out and cancel. Then the remaining will be mr square into theta double dot plus I theta double dot plus kr square theta equal to 0. Here, taking theta double dot as common, we can write mr square plus I whole into theta double dot plus kr square theta equal to 0. Now, as in the previous question, in place of I, we are replacing that using half into capital M into r square. What is capital M? Mass of that particular rotating body. Now, from this equation, let us write down omega n square is equal to kr square by mr square plus half into mr square. How we have arrived at that particular value? Comparing that last equation with the standard equation of what? Mx double dot plus kx equal to 0. For x double dot, we have the term theta double dot here, and for the term x, we have kr square here. Sorry, for the term x, we have theta here. So natural frequency is nothing but square root of the term with the value theta in the numerator divided by the term with the value theta double dot in the numerator. Refer the previous numerical once again. Hence, rearranging and taking the square root, finally we arrive at omega n is equal to square root of 2 by 3 k by m radians per second, and in hertz fn is equal to 1 by 2 pi into square root of omega. The value of omega is root of 2 by 3. Now see, in place of I we have substituted half into capital M into r square, but that capital M is not coming afterwards, after that particular equation. Why is that? Because in this question the cylinder is given as 4 kilogram. That means the mass of that particular cylinder should be taken as 4 kilogram while it is rolling as well as it is translating. So both the terms small m and capital M will become one single value, which is 4000 Newton, which is 4 kilogram. And finally, if you apply the values of k and m in the natural frequency equation, you will get the particular exact specific numerical value for omega n as well as fn. I hope the numericals explained are clear. Please go through the video once again so that every aspect of the explained theory and concepts become much more clearer to you. Thank you guys.